This lecture is about lasers in the laboratory and principally in the world around us. It might surprise you to think of lasers in this theatre, in the home, in the supermarket, on a building site. But you see before you examples of lasers in just those locations, and we should look at some of them. In the theatre, you won't be surprised because you've seen this before. This is just a little laser pointer with which I can pick out that gentleman wearing a red sweater there, this lady wearing a blue shirt there, and because I'm colorblind, I don't know what color that is, but there you are. I can pick out anyone I want by using this quite harmless laser beam. In the home, if your parents were wealthy, you might actually own one of these, and if I angle it just right, you'll see a rather beautiful kind of picture about which we'll talk later. You are much more likely to have in your home one of these. This is a compact disc player, and it plays these rather nice discs, and there is a laser inside there which reads information from that disc to create music. Let's put it on and see what we can hear. Well, that's enough of that. What actually happens there is that a very small laser reads digital information in binary code and then recreates that as sound of a really exceptional quality. The laser which does it is absolutely minute. Here you see the actual laser. The laser is this tiny little dot in the middle of that square there, and you can see how big that is compared with the size of my thumb there. I have the actual device here. That whole assembly you can see there is actually this little tiny thing here, and the laser is the minute little speck that's inside it. Really quite a remarkable device. Well, in the office, we have lasers too. 27 years ago, when Theodore Myman first invented the laser, he could think of nothing to do with it. It was called a solution in search of a problem. It's even been said that he rigged up this ruby laser behind his secretary's head so that when she made a typing mistake, she could push a button on the floor and a laser beam would slice past her ear and erase the mistake that she had made. Now, I don't know whether that story is true or not, but if it is, I would bet that she had pierced ears by the time that she finished. I'd like to introduce you to my secretary, Amanda Jones. Here's Amanda. Now, as you can see, Amanda has pierced ears, not because she uses a laser in the office, although in fact she does. She uses this one, and I'd like to demonstrate that to you. And I need a volunteer to help me, and I know that Sarah is going to help me on this occasion. I'm sorry to have to pre-select, but some training was necessary. Sarah, would you come out down here, please, and sit there? And Amanda will instruct you in what you have to do.
Right, Sarah, if you could just type your name there using the keys. That's great, okay. Now, move the cursor, and I'll just go to you. Move the cursor using the mouse over to the file menu there. Right, click the button down. Now drag it down, right down to print 1. And release the button.
All going? Mm-hmm. What has happened here is we have pre-programmed some information into this computer and word processor, and Sarah has now put some more information in. We've now transferred that into this laser printer. And the laser printer works by having a quite powerful diode laser which writes information on a drum of paper, specially prepared paper. It actually writes the information electrostatically, and then that information is transferred to paper, which is then heat treated to seal the surface. And so what you get out is a quality of print which is really quite remarkable. Now, we did this one earlier. I think I can hear the sounds of the one that Sarah did now emerging. I hope so. Certainly there are signs of life here. And there we go. There's the one she just did, and what it says is presented to Sarah on the occasion of this Christmas lecture, so she can take that home as a souvenir. Thank you very much indeed, Sarah. Thank you, Amanda. Well, when you go to the supermarket, you're likely to encounter a laser again these days, because the till that you use in the supermarket might have a laser in it. The kind of laser used is a helium neon, a red laser, and it scans across in straight lines. And if we have reduced lighting, you ought to be able to see the lines made by the scanning laser. I think we can see that quite nicely. Now, what the laser does is it looks across at some marks on the objects that you're trying to buy, which is called a barcode. And it simply scans across those, and the information automatically and instantly goes into the computer. The barcode you see in blow-up here is just a series of lines of different thicknesses, and the laser scans how thick they are, and that is recorded as a digit in binary code. So you have a series of numbers. An enormous amount of information can be transferred instantaneously into the computer. Well, I thought it might be nice to have a race. I thought we would get two operators to have a race, one using the laser till, one using a conventional till, just to see if there are any advantages. Now, it takes a little training to learn how to use these, so again, I've had to select two volunteers, and we have them up there, Kate and Alison. Kate is going to use the laser till, Alison is going to use this. But we'll make this authentic. Put your overalls on, please. This is a supermarket. And we've got them two basketfuls of identical goods. One there and one there. And we're going to make it a real race, and may the best girl win. So when I get you ready, we'll be ready to go, all right? On your marks, get set, go! What she has to do is to type in the price on every item and then punch a button. What Kate has to do is simply rub the thing over the laser scanning device and stop, we finished. Well, it was close. We only had a very few items, but clearly the laser till won just as well, because that's what we wanted. And if you tear off your checkout slips and give them to me, we'll just have a look. What are the advantages of doing that? Just stay there, that's fine. Come in here, there we are. What are the advantages of doing that other than speed? Well, if you look at this bill, which is the one that Alison had, the conventional till, you can see that every item she punched up just said grocery, and so you don't know what you've bought. Whereas the laser till, because of the information which is on the barcode, actually identifies each individual item. So when you get home, you can check that you really have got all the purchases and they are yours. So it has a lot of advantages for the customer. It has tremendous advantages for the shop, because what has been sold is automatically recorded, and the shelves can be restocked and reordering done absolutely automatically. So these are really quite an advantage, and I think we've just demonstrated that. So I don't think there's any prize really for winning that race, but maybe I can give you a can of baked beans as a prize. How about that? Will you perhaps take your purchases away now? And I think they deserve some applause, don't they, for being very good? laser we just saw was visible. It was a red laser, and the property of the laser radiation we were using was the fact that it travels in straight lines. And I'd like to show you now another such use. But this time we're using an infrared laser, and instead of seeing it, we're going to hear it. And this we would find on a building site. Now, obviously, construction engineers, civil engineers need to make measurements on building sites. They need to measure the heights of various parts of buildings. And the conventional way of doing this is by using a kind of telescope of this sort, which is leveled, and then an assistant would stand at the appropriate point with a pole. You've all seen this happening. And the skilled man, I'm the engineer, would actually line up on a marking on the pole, and then he would make some note. Now, it needs two men to do this, and the man who is holding the pole is the unskilled worker. In fact, he's so unskilled, you can see, he's got the pole on his foot rather than on the ground. So this measurement really doesn't mean very much. How much better to have a machine of this sort? This is a laser leveler, and it has a little rotating diode infrared laser in there, which is now going round and round, spraying out a horizontal beam of quite safe infrared radiation into the room. Well, into the building site, as we're simulating. So now, having set this up, I'm the skilled man, I can now take this pole and go to the point that I want to measure. Should get it the right way up. Here's one place I want to be. So I will get this detector now. I must remember to switch it on. And when I get it to the right height, we should hear an intermittent signal. That means I'm almost there, but not quite right. Now, if you look at your monitors carefully, you should see there's an arrow there, which should tell me whether I should go up or down. Can you tell me whether I should go up or down? Up. Carefully up. I can't go high enough. There we go. That's it. So now I can take the reading, jot it down in my notebook, switch it off, and now I can go to another part of the building. And let's go here, shall we? Somewhere like that. Now then, obviously I'll have to come down now, and again I'll have to remember to switch it on. So let's bring it down. Are we anywhere near? Which way now?
Down.
Which way now? Up?
Up.
There we go. So again, I can make the measurement. And just to show you, it really is the infrared beam which is being detected. If I put my hand in front of the detector, it stops. That's a very, very useful device, which we'll now switch off. And if I make any mistakes, I've got nobody to blame but myself, because I do all the work. Okay. Now, that's fine to make that kind of measurement where you can easily get to the place that you want to make the measurement. You could site that leveler where we want in a building site and walk anywhere. But suppose the thing we want to measure is in an inaccessible place. Suppose, for example, we wanted to measure something in the sky. How would we do that? Well, again, we would use a laser. But we would rely on the fact that laser light is scattered by molecules and by particles, by clusters of molecules. And in order to show that to you, I'd like to do an experiment which was really done in this theatre a long time ago by John Tyndall. I need the screen down for this. What we have here is a simple tank of air and a projector lamp and a mirror. So light from this projector is passing into the tank. There's a reflection from the front surface here, which you see on the screen as the weaker of the two circles of light there. The light travels to a big mirror at the back of the tank, that's down here, and then comes back through the tank, and you see it as the large circle on the screen there. Now there's nothing in this tank but air now. If we put some scattering material in, some smoke, I think you should see an effect. Bryson will now do that for us. And as he does so, I'll tell you what we might expect to see. The size of particles which are being produced in that tank are such that they scatter blue light more than they scatter red light. So all the blue light is being scattered away, and the red light is being transmitted. So this disk of transmitted light you can compare with the front scatter, which doesn't change color, is gradually looking redder and redder. And I think if we see that in subdued lighting, we might see it more clearly. I think you can begin to see that there's a reddish, which is actually a brownish color at the moment, but it would go red. That's the reason that the sky looks red when you see a sunset, because all the blue light from the sun is being scattered away from the, by the atmosphere, and just the red light is coming through to your eyes. John Tyndall knew that, and he was the first to explain it in the last century. Well, we can use the scattering of light to measure particles, to see where particles are. Let's just show you how we might do that with a laser. Here we have a well-known company, which we hope will make a lot of money. And Bryson, I think you should turn on the boilers of this well-known manufacturing company. And there we have some smoke being produced. Now, if I want to know where that smoke is going and how thick it is, I could use a laser. I could simply take a laser and switch it on, and I think you'll be able to see the light being scattered by the smoke as it comes out of this chimney. Can you all see that? And if you time how long it takes for the laser pulse to go out to the smoke and back again, you can range, you can see through different thicknesses and get signals at different times coming back. That's called ranging. It's just like radar, radio detection and ranging. This is light detection and ranging. It's called Lidar. Well now, what I'd like to show you is a van which belongs to the Central Electricity Generating Board in research laboratories in Leatherhead, and it was parked outside the Royal Institution. Here you see the laser, which is now firing, very powerful laser. The light is steered by a mirror up through the roof of the van and into the London sky. And the backscattered radiation, you can see here, is mainly being scattered from this level, which is about 500 meters above Albemarle Street. And there you see it in close-up. This is a thickness of cloud. This is the cloud layer over London. You can see what happens above here is just noise, and the signal gets noisier because most of the backscatter has already occurred in this point. So these people can sit in their van, squirt a laser into the sky, and look at clouds of anything. It can be smoke from power stations, it can be smoke from other chimneys, it can be clouds. Very clever device. This idea of looking at scattering from moving particles is widely used elsewhere. You can see over there lasers being used to look at droplets coming from a nozzle. There's a nozzle squirting water and crossed laser beams at the bottom, and where the water droplets are present, you see very strong scattered light. That technique is called laser anemometry, and it's used, for example, to study blood flow, flow of all sorts of fluids, including gases. Now, looking at droplets in the sky is fairly easy, as I've shown you. I made it look easy. But it doesn't tell you what the droplets are or what the other molecules are. If you could use two lasers, you might be able to do that, because you could send one laser beam up which is not absorbed by any of the material there, and another color laser which is absorbed by one of the constituents you're interested in. And if you just compare those two signals, you get the absorption of one. It's a differential technique, and it's got the terrible name of dial, differential absorption Lidar, and it's used to look at the constitution of what comes out of smokestacks, for example. Well, what might come out of smokestacks? If you're in the power generating industry, what you burn, something like this. This is the kind of stuff that is burned in a power station. That's actually a very light fraction of crude oil, and what is actually burned is much heavier and thicker and dirtier than that. Or you might burn this, which is just coal. It wouldn't be burned in that form, it would be powdered. But when you burn those materials, you also burn some of this. Those hydrocarbon fuels contain as much as 2%, sometimes more, of this substance, which is sulfur. And when you burn sulfur, you produce something which has become infamous. And let me just do that. That should go nicely now. If I burn it in there. The sulfur burns to a gas, very pungent smelling, colorless gas, sulfur dioxide. Sulfur dioxide reacts in sunlight to make sulfur trioxide. Sulfur trioxide dissolves in water to make concentrated sulfuric acid, and that's one of the constituents of acid rain that we've all read about. Now, sulfur dioxide coming out of smokestacks can easily be sensed by using this differential Lidar technique, and an equivalent van to the one we just saw is used to monitor sulfur dioxide many kilometers away from the source, and it helps the scientists with the Central Electricity Generating Board to understand the chemistry of what is going on in the atmosphere. So that really is a form of spectroscopy, and I really would like to turn to spectroscopy now. When you see dyestuffs like the samples we've already seen before, these absorb different colors of light because the chemical composition of the molecules is quite different. These are very different molecules, and so they absorb different colored light. And by measuring exactly what color of light is absorbed, you can tell what molecules you've got, if you're lucky. And if you measure how much light is absorbed, you can see how much of that particular molecule you've got. And that's really an analytical technique. But the absorption technique has problems, as we'll try and show you. I need somebody to help me do this. Perhaps the boy there, can you come down? Fine. And what's your name? Jacob. Would you like to put those gloves on, Jacob, because you're going to get this stuff on your hands. You can do a very, very simple experiment. We have here rather filthy looking dye stuff in concentrated solution, and all I want you to do is dilute it. So I want you to pour a test tube full of this stuff into there, and then drop it into that, pour it into this beaker here. And I'll take the stirrer. Are you good at chemistry at school? No? Well, you will be after this. Now then, come round the back beside me and just pour it into there. Now what we've taken is 10 milliliters of that concentrated solution, and I'll stir it up, and this is 1 liter, so we've diluted that by 100 times. Now I want you to just put that right in to fill it up again. That's why you've got the gloves on. All right. Is it full? Now just pour it into there. Okay. And now we'll stir it up again. So now we've diluted that by another 100 times. So that's a 10,000 dilution so far. Now I want you to do it again. Okay, in we go. Right. Now, that's what, another 100 times? So that's 1,000,000 times dilution, isn't it? Now, can you see, we started out with something that looked that color, we've diluted it 1,000,000 times, and now you can't see the color. It'd be very difficult to make an absorption measurement on that. With any luck, however, when we look at it in fluorescence, which we'll do now, if you could stand back, Jacob. When we put the lights down, let me take this one out of the way. I can still see a faint fluorescence there. Can you in the front see just some? Wasn't easy to see any absorption. We can see fluorescence. But we have instruments which can see single particles of light in fluorescence. So fluorescence is a much, much more sensitive technique than absorption. So if we can't rely on absorption, then we come to use fluorescence to analyze very, very tiny amounts of material. Thank you very much indeed. I think you should go to the top of the class for your chemistry. Now, analytical techniques like that have enormous use forensically. That is, when scientists are trying to solve crimes. And I would like 4 people to help me help me commit, first of all, a crime. Now then, who can we have? We'll have one here, please. Another one there, please. Oh, one there, please. Now, how have we got? We've got 2 boys and 1 girl. We need a girl. Perhaps the lady on the front. All right? That will do. Now, you just stand in front here. Can we form a line all the way along? There we go. Right. Now then, suppose you wanted to bump her off. You might use poison, mightn't you? Might use a drug. So what would happen to her when she was dead would be that a pathologist would take the organs from your body, your liver and stomach and all the other bits, and grind them up and then make a solution and would use an instrument which would measure the fluorescence that is there, because the color of fluorescence that was there might tell the pathologist what drug had been used to kill you. Well, I thought we might do a crime here, but maybe not murder, because it's a bit one way, isn't it? Let's do some petty larceny instead, shall we? Behind over there, you'll see a wallet, a purse, and when I turn my back and hide my head, I want one of you 4, you look like criminals, I think, yes, one of you 4 has to steal that wallet, and then I want to tell you which one it was that stole it. Are you very clear what's going to happen? Just one of you will go and take it, and then I'll try and tell you which one took it. Well, I'm going to go and hide now, all right? And you have to shout out when you've done it. Put it somewhere where I can't see it afterwards.
Okay.
All done? All right. Come on round here into the bite of the bench, and I want to try and show you. There you go. Come right forwards. That's it. Now then, all I want you to do is to put your hands up above this black thing like that, and then we ought to be able to see who took it. Now, can we all see that? Oh, yes, there he is. There's the culprit, yes. This one here, I think. Caught you red-handed or yellow-handed or blue-handed or whatever it is, right? There we go. Constable Gore, please take this man off to the restaurant. That might look very silly, but there is a technique of looking for fingerprints on rather difficult places, which uses lasers to scan. And you can take fingerprints in really quite difficult circumstances, and that has been used to prosecute many people. The police don't want me to tell you how it's done, because if I tell you how it's done, everybody will know how it's done, including the criminals. So that's all I can say. When the chemical composition of things is very different, the color of light which is absorbed is very different, and the color of light which is given out as fluorescence is very different. But when the structure of molecules is very similar, the light which is absorbed will be almost of the same color. And trying to select one molecule becomes difficult. It's like having two radio stations very close together, and you can't really selectively get them. See if we can do that. If I tune on the dial here, I've got two stations at the same time there. If I tune very, very carefully, I might be able to make it clearer. Got it. Got it. That's perfectly understandable, isn't it? Well, it is to Professor Thomas anyway. I mean, I was able carefully to select just one station, and I'd like to be able to do that with molecules too. So, what you have to selectively tune into a molecule is a fine-tuning laser, but I also have to have that the absorption bands of the molecules don't overlap too much. Now, if the structure of the molecules is almost the same, then they will overlap. Here are two molecules which are almost the same. They're called xylenes. If a substituent group is in that position, it's called metaxylene. And if the substituent group is in that position, it's called paraxylene. Almost the same molecule. One absorbs in one region, one color of light, the other there, but they're very overlapping, and it doesn't matter how pure a laser I use to try and excite one of them, I will always excite the other. The only way I can selectively excite is if I make the absorption bands much narrower. So what I have to get is something like that. There's one absorption band, there's the other. Now I can tune into either this one or that one, just as I did in the radio station. Right? Here is an actual result. These are these compounds where I have been able to achieve this separation. This is a result of Professor Robert Donovan of the University of Edinburgh. There's paraxylene, there's metaxylene, and you can see they're very different. They're absorbing different regions of the spectrum. Now, how do we get that separation? Because you start off with them being very overlapping. The answer is we cool the molecules down. If you cool the molecules down, you can make those absorption bands narrow. There are some other advantages in cooling down too. There is a dye stuff on a filter paper, and I can show you that it doesn't fluoresce at room temperature. There really is no fluorescence there. But if I cool it down, and I'll do so with liquid nitrogen at minus 196 degrees Celsius, it's very cold, then with any luck, I should be able to make it fluoresce. Also makes a rather nice mess. Now, I think you can probably see that that does fluoresce quite nicely now. Can you see that? If I put my hand on it, I made it rather cold. So we do it with this hand. I've got frostbite now. There, you can see as I warm it up, the fluorescence stops. So that cooling it down has the advantage of narrowing the absorption band, but also of making it fluorescent so we can detect the molecules much more easily. Now, I have to tell you that this demonstration was told to me by a very improbably named young man called Lloyd A. Bum in Chicago about 5 years ago in the United States. And he claims to have observed this first when, as he put it, he was fooling around with liquid nitrogen in his bathroom, and he spilt some liquid nitrogen on the bath mat, which started to fluoresce. The mind boggles what he was doing with his liquid nitrogen in the bathroom. We can cool things by expansion, and I can show you that quite easily just by expanding this carbon dioxide from a fire extinguisher into the air. When I do that, I lose the audience over there. Let's do it again. I like doing that. That gas was cooling so much it was turning from a gas into a solid. That's why you saw the smoke. And then as the solid evaporated again, it disappeared. Now, we don't want it to go solid. We want to keep it as a gas. And we can do that in a special way of cooling it by mixing the thing we want to cool with helium and then sucking it through a small hole. And down below in the research laboratories below us, there's an apparatus which does just that. This is a very large pump. it pumps at a speed of 7,000 litres per second, and it pumps gas through a very small hole, about 100 millionths of a metre across, and that cools the gas down to a temperature which is just half a degree above absolute zero temperature. So the gas ends up at being about minus 272.6 degrees Celsius, minus 272.6. And then we fire a laser up this tube and investigate the molecules, the cold molecules, using this laser. Now, it's a very curious system because the gas is very cold, but the molecules are still moving quite fast. They're moving at speeds in excess of the velocity of sound. That's worth exploring. Velocity of sound, as I'll show you, is not constant because
the velocity of sound depends upon the medium in which you create it.
What I said was the velocity of sound depends upon the medium in which I create it. And what I was creating it in there was largely helium, but there was a good amount of ethyl alcohol in there too, actually. The experiment I showed you on the xylenes was not really done with fluorescence. It was done with an equally sensitive technique called ionization. And let me show you that. In ionization, all that happens is that if we take a simple model of an atom, central nucleus, an electron around it, when the light falls on the molecule, the electron is removed completely. And so what one is left with is a positive charge there. And you can, whoops, oh, I like it, a positive charge there. And you can count those positive ions very easily. So it is as sensitive a technique as fluorescence. Now, you can separate some molecules at room temperature. You don't have to cool them down. Some atoms are of particular interest. If you want to make a nuclear fission reactor work, you use uranium as a fuel. And uranium has two isotopes of importance. An isotope is just the same chemical element with a different mass. There is uranium-238, which is the biggest one there. It's there in the greatest amount, and it's not the one you want. The one you want is uranium-235, which is the radioactive one. Now, many reactors won't work on normal, natural uranium. You have to increase the amount of uranium-235. And one of the ways of doing it is to excite selectively, using a laser, the uranium-235, collect the uranium-235, and so enrich the uranium isotopes. And then you can use that as a fuel. This is actually a commercial process used in the United States to provide uranium for power station generation. What you're really doing is selectively tuning into the two uranium isotopes. Now, what we have here, when we get it lined up, there we go. We have two small helium neon lasers which are impinging on mirrors, and I think we ought to be able to see them. Can you see the laser beams traveling along? And just in front here you might be able to see the beams there. The light is being reflected from these small mirrors over onto the screen behind. This is a sound analogy again. If we now turn up some sound and make these hacksaw blades vibrate, because they're different lengths, they have different frequencies at which they would resonate. And so as Bryson scans through some different frequencies, we ought to be able to make one spot of light vibrate preferentially. There you can see one is really vibrating quite fast. As he changes the frequency, the other one will start to go. And if we used a broadband, we might be able to get both to go. There we are. I think that's probably enough explanation. We can choose a frequency which would just excite one of them. That's exactly what is done with the uranium. You select the one isotope of uranium and enrich the fuel. Now, when you've got your power station in operation, your nuclear fission power station, the fuel elements get radioactive, get very hot. And you can't inspect them. You can't send an engineer in there to look at them because the radiation is dangerous. But there is a technique you can use now to inspect such awkward places, and it uses a very special kind of photography, which we'll talk about now, which again uses lasers. And so we have Mike Anderson from Holomex to demonstrate to us a rather splendid kind of camera which he has developed, which takes photographs of a very special kind. Right. Now, I'd like somebody to help me do this because we want to make sure he doesn't cheat. Perhaps you would come and help me, would you? What's your name, please? Kevin. You'd like to come round here, Kevin? We're going to place an object in there, and he's then going to take a hologram, as it's called, of the object. But we want to make sure he doesn't cheat. So here's the object. What I'd like you to do is to set the hands of the clock to whatever time you choose, and then we'll tell the audience what it is, and we'll record it so that Mike has no chance of cheating. So what's that? That's 10:30, I think. Is that right? Good. So now I'm going to place that in position there. And in there is a small helium neon laser, and we need the lights right down to be able to see it, I think. It really is not terribly powerful, but you can see, I think now, scattered radiation, red radiation from the red laser. Now, you can take a photograph using that, but then the photograph has to be developed in the normal way, and that has to be done in the dark. So Mike is going to go away now and do that, and you're going to go and make sure he doesn't cheat, and we'll see you again in a short while. Thank you very much. Okay. And while they're doing that, I'll explain what is actually going on. Light from a laser really acts as though it was one single wave starting out at the same point in time, one single point in time. And all they do to take that photograph is to take the laser beam and split it in two. So one part of the laser beam goes directly to a photographic plate. The other goes from the laser to the object, and you see we have the same object that we have put into the camera, and then is reflected off back to the photographic plate. And what happens on the plate depends on how far this one has traveled. Because if the wave from this one gets in at the surface in, let me try and get it right for you, a position like that, where the two maxima coincide, then there's an intense spot of light on the plate, and so the emulsion will be developed, will change. If, however, the maximum from the scattered light coincides with a minimum from the direct laser light, then the two things just cancel out. You get no light there at all. That's called destructive interference, and so you won't get anything developing on the plate. Now, the light from the object is being scattered from all of the object in 3 dimensions. And so what you have got on the photographic plate is a record, an interference pattern of every point on that object. So you can recreate the object simply by looking at that with the same colored light that you used to create it. That's what's called a hologram. And Edward Tidder from Laser Holograms has brought along some beautiful examples to show us. And I think I'll come round and inspect some of these with you. Now, here is one which I think you should be able to see, certainly we'll see on the monitors. This is of Pegasus, the winged horse, and you can see it's 3-dimensional as I move it around. It gives you a 3-dimensional image. This one is old technology, which is slightly less good. This is of a bee on a rose. Can you see that? This one is really rather beautiful. It's of some fan blades, turbine blades against a wall or a background. And it's very clever because if I turn it all the way around, there's a different view on the back. But if you look, there's nothing in between. Really rather clever. Here's somebody some of you might recognize. Looks like he's in pain to me. This is a rather nice object. Remember the laser tills that we looked at? There the lasers were scanned by a series of mirrors. In future, the lasers will be scanned simply by bouncing off this one disk, which is holographically made. And finally, of all these lovely objects which I can show you, I thought I might show you these, a pair of rather fun spectacles, which I can now put on for you and play the fool. Fine. Edward, thank you very much for coming. Now, let's go back to our nuclear power station. An engineer can now take a hologram of the fuel rods in a nuclear power station and inspect this three-dimensionally. He can actually look for wear in the fuel rods. Doesn't ever have to go near it. He can do it remotely. And this gives you one instance of the many industrial applications of holograms, of holography. Such a power station acts by nuclear fission. Power stations of the future might use nuclear fusion, just like our sun does, where you burn together isotopes of hydrogen into helium. You change them from one element to another. Now, to do so, you have to create tremendous pressures and temperatures. And one way of doing that is to use lasers. This is a rather old film of a project in California where many very powerful lasers, you can see the scale of this thing by the size of these people in the gantry. Each of these is a very large neodymium laser amplifier, and the output of all of these lasers is fired simultaneously at a target. The target is housed in this great stainless steel chamber here. The target itself is a tiny little pinhead full of tritium, deuterium, and the isotopes of hydrogen. When the lasers fire on this poor defenseless target, they create temperatures in excess of 100 million degrees centigrade and huge pressures, and that is just about enough to create nuclear fusion, and that would create energy, and I believe that may be the energy source of the 21st century, but it's still in the experimental stage at the moment. Inevitably, the enormous power of lasers has led to their use as weapons. In fact, lasers in military use have been around for a long time, principally as guidance systems. Now, who's going to help me demonstrate that point? Who's fired? Put your hands down first of all. Who's ever fired a rifle before? All right, you put your hand up first. You can come and show me. This is really quite heavy. Let's suppose you are somewhere in the Gulf, let's say, and there is something which is threatening you. It's a ship of some sort, and you want to destroy it. Now, I'm not suggesting you can destroy it with a rifle, but you can get it destroyed by guidance. Now, can you see now that you've got on the sight here, you can aim it if you like, but you might get tired, so perhaps just hold it like that. He's now got a spot of light which is aimed at that target, and the laser light is scattered back. Now, if he arranges that a missile fired somewhere far away is guided onto that target now by the reflected light from the laser, we might be able to destroy this threatening ship. Shall we go? Fire. Oh, very good. I like it. Thank you very much indeed. Thanks a lot. Well, the people on the ship were so frightened they blew themselves up when they saw the missile arriving. If you wanted to destroy an object, a material, what would you use? Well, you could in fact use infrared radiation. Infrared radiation, we know, makes put it that way around. Makes things vibrate. If we illuminate this object, a crystal, with infrared radiation, we should be able to make it vibrate quite nicely. And if I turned that up far enough, I could make it vibrate enough that it fell apart. I could destroy it. So infrared radiation might work. It might be better to use ultraviolet light, because ultraviolet photons carry much more energy. We can perhaps simulate that. If I irradiate this crystal with ultraviolet light, I should be able to break all of the chemical bonds that hold these atoms together and make them all fly apart. Let's just see if I can do that. 1, 2, 3. Well, not bad, was it? I mean, most of it broke apart. But that ablation happens instantaneously. It happens in 1,000th of 1,000,000th of 1,000,000th of a second, and the atoms just fly apart. We could go even higher and use X radiation, and that is what is proposed in the Strategic Defense Initiative of President Reagan. It's proposed to have battle stations in space like this one. This actually is a particle beam weapon which fires particles, charged particles, at incoming rockets from the other side, ballistic missiles, so that when this weapon fires, it destroys the incoming rocket. Now, it can either be particle beam or it can be lasers of various sort. This is a mock-up of the particle beam weapon which had been proposed. This is a mock-up of the laser-driven variety, where the very intense laser radiation can be fired at fast-moving ballistic missiles. Now, I personally think there's a lot of dangerous nonsense in this, because although these weapons can be developed, the guidance system and tracking systems for them are beyond the capability of the present generation of computers. We would have to develop new computers in order to use these things effectively. And such a computer might be an optical computer, for example, using laser light instead of electronics. But I think the situation is such that the measures taken by the attacking side to counteract these defensive measures can really be quite inexpensive. Let me just symbolize that by showing you a very simple experiment. We'll use an infrared laser. We'll try to destroy an enemy missile, which happens in this case to be painted black. When I put it in front of the laser beam, let's just count how long it takes for it to be destroyed. I'm moving it across now. 1, 2, 3, 4, 5. It's moving. Oh, I wish it wouldn't do that. 6 or 7. This one has simply been polished. If I turn it round, having been polished, it will reflect the laser light. Let's just steady it and get it in position. Switch it on now then, Bryson. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's disappointing, isn't it? It's not going to go, simply because the radiation is being reflected away. Now, it's a very simple thing to do that, and so you could make it necessary for the defending side to have to invest so much power, so much money in the kind of laser that would inevitably destroy a rocket of that sort, that I think this really is just the figment of somebody's imagination. I really don't think it will work. Let's end on a rather more peaceful note. Let's recreate a modern version of an experiment first done 100 years ago by Charles Wheatstone. He astonished his audience by pretending to play a cello and placed it on a wooden rod, and from the cello came not cello music but piano music. What was happening was the music was being created down below, was passing up the broomstick was used, and this was just acting as a sounding board. If I take it off, it stops. Now, if I wanted to recreate that experiment today, of course I would use a laser beam. And so we will pass laser light up this Perspex tube, and we will listen to it with the aid of a diode, and with any luck we'll be able to hear some piano music. Well, it sounds pretty horrible, but there is indeed some music there. And if I interrupt the laser beam, the music stops. That technique is used to eavesdrop on your neighbors. You can listen to a vibrating window and pick up speech a long way away. It's used in the Navy to communicate with submarines really rather accurately. Now, I hope that we should have our volunteer right at the end with the result of the experiment we did earlier, which is to make the hologram of the clock. Can you all see? The clock is indeed set at 10:30. Did he cheat? He didn't cheat. Isn't that wonderful? So there we are. We've made a hologram in front of you. And I think that's probably a nice way to end this lecture. I'd like to give you all souvenirs, as you know. If you open the envelopes, you'll find your own personal hologram. Have you all got them? Stick them on your foreheads, and that's the end of the lecture. Thank you very much indeed. Thank you.